After watching this video lecture, students will be able to calculate mole fractions and use Dalton's law to calculate the partial pressures of gases. Dalton's law states that the total pressure of gases inside of a container at constant volume and temperature are going to be equal to the sums of the individual partial pressures of each gas. So if we have gas number 1 and gas number 2, we combine them and put them in a single container. The partial pressure that is exhibited from the gas 2 and the partial pressure that's exhibited from gas 1, if we sum those two values, that will give us the pressure value of the newly combined gases in the container. Okay, and once again, guys, this is at constant volume and temperature. Now we can use Dalton's law of partial pressures and this relationship that we see here, the pressure total equaling the partial pressure of one gas plus the partial pressure of another gas, and our understanding and relationship of pressure to the ideal gas law to get something called the mole fraction. So the mole fraction is the number of moles of a specific gas divided by the total number of moles of the gas in the container. So the mole fraction of A will be calculated, gas A will be calculated by taking the number of moles of gas A and dividing by the total number of moles of gases A and B combined. Okay, and the same concept applies to the mole fraction of B. Okay, you're going to take the number of moles of gas B and divide it out by the total number of moles of gases in that container. So we can then take this mole fraction, and the mole fraction will allow us to figure out the individual pressure exerted by a specific gas in a container, given both the number of moles of the gases in the container and the total pressure. So if we look at this setup here, we can figure out the partial pressure of A by taking the mole fraction and the pressure total, multiplying them together, and that will give us the value that we desire. Same thing is true with the mole fraction of B times the total pressure. That'll give us the partial pressure of B. So in a generic way, the partial pressure of a specific gas will be equal to the mole fraction of that specific gas times the total pressure. So basically, it's kind of like looking at the decimal form percentage that each gas occupies within a specific container and then multiplying it by the total pressure. So let's go ahead and let's look at some practice problems. So the problem here tells us that we have a sample of natural gas. So we have a container with some gas that contains 8.24 moles of methane, 0.42 moles of ethane, and 0.116 moles of propane. Okay, it tells us if the total pressure of the gases is 1.37 atm, what is the partial pressure of propane? So we've been given our number of moles of each of the individual gases in the container, and we've been given the total pressure basically caused by those gases in that container. Right? So what they want us to figure out is the partial pressure of propane. So we know that the relationship between the partial pressure of a specific gas is equal to the mole fraction times the pressure total. But we've been told that the pressure total is 1.37 atm. Okay, and we've also been given enough information about the various gases in the container in order to calculate the mole fraction. Okay, so in order to get the mole fraction for the propane, we are going to go ahead and take our number of moles of propane, which is 0.116. Okay, and we're going to divide it by the total moles of all the gases in the container. Okay, so 8.24 moles plus 0.421 moles plus 0.116 moles. Okay, basically plug this into our calculator and we get 0.0132. Okay, that's our mole fraction. So then we're going to take our mole fraction and plug it into the equation up here. So the partial pressure of our propane is going to be equal to 0.0132, which is our mole fraction, times our total pressure. Okay, we plug that into our calculator, and that's going to give us 0.0181 atm. Okay, so the pressure that is being exhibited by propane is 0.0181 atm. So basically, of the pressure that's being exhibited, or the total pressure that's occurring in that container, 0.0181 atm is coming from the propane. And we could subsequently use the rest of the values and the rest of the mole fractions for the other gases involved to figure out the remaining partial pressures of each. So the question we have here is a two-parter. Okay, so it tells us that we have a 2.5 liter flask at 15 degrees C that contains a mixture of argon, neon, and helium at partial pressures of 0.32 atm, 0.15, and 0.42 atm for each of the individual gases. And they want us to calculate the total pressure of the mixture. So the first part here for A, we know that we're going to be using Dalton's Law of partial pressure. So P1 plus P2 plus P3. So in this case, we're just going to be summing up our individual pressures. Okay, so they've given us 0.32 atm, and they've given us 0.15 atm, and they've given us 0.42 atm. Okay, now guys, if they give us all of these partial pressures in the same values, we can do a direct summation, but please make sure that all the units are the same. You can't add up atm and torr. You'd have to do a pressure conversion before you plug this into the equation. So if we plug this in our calculator, this is going to give us 0.89 atm. Okay, so this is the total pressure of the gas that's in this container, this 2.5 liter flask at 15 degrees C. So the question in part B is a little bit more complicated. In this case, we're going to use our information in our ideal gas law in order to calculate the number of moles present for each of the gases being expressed in this question. So because of the fact that they tell us that we are going to remove the argon, we are going to basically skip the mole calculation for the argon because it's no longer present in our substance, or in our container rather. So instead what we're going to do is we're going to use this equation, okay, the ideal gas equation related to, or solve for the number of moles, and we're going to utilize our values for He and neon in order to calculate the number of moles present in each. So we have 0.15 atm times 2.5 liters divided by our constant, mole Kelvin, okay, and then times our new temperature, or excuse me, our old temperature, which is 288.15 Kelvin. Okay, this is going to give us the following number of moles of helium. Okay, we're going to do the same thing for our neon. Okay. Okay, and this is going to give us the following value for our neon. Okay, so now we have the number of moles that are in that container at that temperature for each of the gases that are originally there. Okay, so now we've removed the argon, so we don't care about the argon anymore. But what they're asking us now is the new volume of the container at STP. Okay, so what we're going to do is we're going to sum together these two values, right? And we're going to utilize the relationship between a volume and the number of moles at STP. Okay, so if we take these, Okay, we're going to sum those together. Okay. And we're then going to multiply this value, because these are obviously our number of moles, times our 22.4 liters per mole. Okay, and that's going to give us 1.346 liters, or 1.3 liters that those remaining gases will occupy. So a lot of times when we are collecting gas samples, we do so by water displacement. And if you look at this setup here, we have a reaction mixture that we're heating. We have it connected to basically a container that's been filled with water and inverted in a tub of water. Okay, and basically as the reaction proceeds and gas is being expressed from the reaction, it's then collected in the bottle that's here. Now, as we're collecting gas, sometimes some of the, depending on the temperature of the reaction conditions or temperature of the room, rather, the water that's in the container will also vaporize. And basically, you're not just trapping oxygen or whatever your product gas is up here, but you're also trapping some water vapor. So whenever we're collecting a gas over water, we need to account for that water vapor pressure. So the pressure total, or we'll use Dalton's law here, but the pressure total in this case is going to equal to the pressure of the gases that are collected plus the water vapor that might be also contained in the bottle. Now, when the bottle's height is adjusted in the tub of water, basically what you end up doing is equalizing the atmospheric pressure to the pressure of the gases that are in that container. So if we know our atmospheric pressure when we utilize this type of setup, we can subsequently figure out our pressure total. You know, as your temperature is increasing, the production of your water vapor is also going to increase. So in order to figure out what our water vapor pressure is, we would basically need to know our temperature, and we subsequently would use a table like this. So if we know what our temperature is, we can figure out the water vapor pressure that is basically being expressed at that time, and we can plug this value in for our pH2O as seen in the equation previously. So if we know the temperature, we can use this chart to figure out this value. So given this problem that we have here, we've been told we have a mixture of helium and neon gas, and that has been collected over water at 25 degrees C and a pressure of 745 millimeters of mercury. If the partial pressure of helium is 368 millimeters of mercury, what is the partial pressure of neon? Okay, so if this process, in this process rather, we were told that we are collecting over water at 25 degrees C. So we know that our equation is going to be as follows. Plus P of H2O, right? Because we're collecting over water. Now we know our temperature, so we go to that chart and we figure out that our pressure over H2O is as follows. Okay. We do know our pressure total because we know our atmospheric pressure. Okay. We also know our pressure of our helium because that's been given to us. Okay, so in order to calculate for pressure of neon, we're just going to do some very simple math. Okay, so basically our P total is going to be subtracting our pressure of our helium and our pressure of our H2O respectively, and that will leave us with our pressure of our unknown neon. Okay, so if we go ahead and we plug all these numbers in, so 745 millimeters of mercury minus, let's see, 368 millimeters of mercury, okay, which is our pressure over helium, plus 23.76 millimeters of mercury. Okay, this will give us our pressure of neon. So from our calculator, this gives us 353.24 millimeters of mercury. Okay, or if we consider sig figs based on the fact that we're doing addition and subtraction, this is just going to give us 353 millimeters of mercury. Okay, so whenever you're collecting over a gas, you want to make sure that you're considering the partial pressure of that water vapor, and of course you're getting your pressure total from your atmospheric pressure. So the problem we've been presented with here is basically a reaction that we're running. It's producing a gas that's being collected over water. So we know that we've been told that we're doing our collection at 25 degrees C. So we already know that our pressure of our H2O is going to be equal to that 23.76 millimeters of mercury. So we know that the pressure of the gas in the container, that pressure total is going to correspond to the value we have here. So P total is equal to the 0.980 atm. Now, if we consider Dalton's Law of partial pressures for gases collected over water, we know that this is what the equation looks like. Okay, we know this and we know this, so we can subsequently figure out the pressure of our gas. Okay, so basically what we're going to end up doing is subtracting out our partial pressure of our water from our pressure total. Okay, but in order to do this, we need to make the units match. Okay, so we have atm in millimeters of mercury. If we go ahead and convert our millimeters of mercury to atm, we end up with 0.03126 atm. Okay, and those are just basic conversions using the 760 millimeters of mercury to 1 atm ratio. I would normally show that work, but we're going to run out. We potentially will run out of some room here. So we're going to use that value. All right. So the pressure of my gas that I actually collected, that hydrogen, is going to be 0.980 minus 0.03126. Okay, atm. All right, if we do the subtraction in our calculators, we end up with 0.9487. Okay, and so this is our pressure of our gas. Now they want us to tell them the number of grams of zinc metal consumed. So we know that we're going to need to take advantage of a mole ratio here at some point in time, so we know that we're going to need to get into moles. So if we take the information that we've calculated so far, our pressure of our gas, our temperature, etc., we can use our ideal gas law and subsequently rearrange it and get ourselves our number of moles of hydrogen gas produced. Okay, so we plug in our numbers, okay, our new pressure that we figured out. That goes here. Our volume is 7.80 liters. Okay, we have our constant. Okay, and of course we have our temperature, which is 298.15 Kelvin. Okay, we plug all this into our calculator. All right, and we get 0.3023. Okay, moles of H2. Okay, now they are not asking for information about H2, moles of H2. They're asking for grams of zinc. So we're going to have to use a mole ratio at this point in order to go from moles of H2 into moles of zinc, and subsequently from moles of zinc to grams of zinc. So we're going to have our 0.3023, okay, moles of H2. Okay, and then we need our mole relationship between H2 and zinc. And if we look at the equation above, okay, we have a balanced setup, and we know that our relationship between H2 and zinc is 1 to 1. So we're still going to show this step even though it's a 1 to 1 setup, okay, because we need to show that, hey, we understand a mole ratio is necessary. Okay, so this will put us into moles of zinc. Now, they don't want moles of zinc, they want grams of zinc, so we're going to use the molar mass of zinc in order to calculate our values. So if we plug all this into our calculator, we're going to end up with 19.8 grams of zinc. Okay, so in this problem, guys, we have used Dalton's Law of partial pressures in order to figure out the pressure of a gas that's been collected in a chemical reaction. We subtracted out that partial pressure of that water vapor in order to get the pressure of that gas. The pressure of that gas can then be plugged into the ideal gas law and basically allows us to solve for the number of moles of that gas. Once we know the number of moles of that gas, we can then figure out other things about this chemical reaction using stoichiometry. So we could have figured out how much of the HCl we used. We could have used how much zinc chloride should have been produced. We could have figured out a lot of different things, but they asked us to figure out how many grams of zinc metal. So we used the relationship or the mole ratio between zinc and hydrogen gas to get us into moles of hydrogen gas. And then we used the molar mass of our zinc in order to calculate our total number of grams of zinc produced.